The calcium in your bones was forged inside the core of a star that no longer exists. The oxygen you just breathed was manufactured billions of years ago in a nuclear furnace so hot and so extreme that nothing on Earth has ever come close to replicating its conditions. The iron carrying oxygen through your blood right now, at this exact moment, was created in the final violent seconds of a star's death. An explosion so powerful it briefly outshone every other star in its galaxy combined. You are not simply living beneath the stars. You are, in the most literal chemical sense available to physics, made of them. This is not a metaphor, and it is not exaggeration for the sake of wonder, though it happens to be genuinely wonderful. It is a precise, quantitative claim, verified through decades of careful astrophysics. The vast majority of every element heavier than hydrogen and helium, the carbon that forms the backbone of every molecule in your body, the nitrogen in your DNA, the calcium in your skeleton, the iron in your blood, the phosphorus in every cell membrane keeping you alive right now, was created inside stars through nuclear processes that can only occur under the extraordinary pressures and temperatures found in stellar cores or in the catastrophic split-second violence of a star's death. The universe in its earliest moments contained almost none of this. Immediately after the Big Bang, as we explored in the previous chapter of this series, the cosmos consisted almost entirely of hydrogen, helium, and a trace of lithium, the three lightest elements, forged in the first few minutes of cosmic history. Nothing more complex existed anywhere. No carbon, no oxygen, no nitrogen, no calcium, no iron, none of the chemistry that life as we understand it absolutely requires. Everything else, every element on the periodic table heavier than lithium, everything that makes complex chemistry and therefore life possible at all, had to be built somewhere, sometime, through some process the early universe itself was not hot or dense enough to sustain for long. That somewhere was inside stars. And tonight, we are going to trace the complete arc of a star's existence, from the cold, patient clouds where stars are born, through the long, stable middle of their lives, to the specific, varied, sometimes catastrophic ways they die, because scattered throughout that entire arc, at every single stage, is the answer to where you, quite literally, came from. Let's begin in the coldest, darkest, quietest places in the galaxy, because that is where every star, including our own sun, actually begins. Scattered throughout every galaxy, including our own, are vast cold clouds of gas and dust drifting through interstellar space, largely unremarkable, often invisible except in very specific kinds of light. Astronomers call them molecular clouds, and they represent the raw material from which every single star in the universe has ever formed. These clouds are composed primarily of hydrogen, the same primordial element forged in the first minutes after the Big Bang, along with helium, trace amounts of heavier elements produced by previous generations of stars, and fine grains of dust. They are, by the standards of everyday physics, extraordinarily cold, often just a few degrees above absolute zero, and extraordinarily diffuse, far emptier than the best vacuum humans have ever created in a laboratory on Earth. And yet across a molecular cloud that might span dozens or even hundreds of light years, the total accumulated mass can reach hundreds of thousands or even millions of times the mass of our Sun. For long stretches of time, these clouds simply drift, held in a delicate, unstable equilibrium between the inward pull of their own gravity and the outward pressure generated by their own internal heat and turbulent motion. Left entirely undisturbed, a molecular cloud might persist in this state for a very long time. But molecular clouds are rarely left entirely undisturbed. A nearby supernova, the explosive death of another star, a subject we will return to later tonight, can send a shockwave rippling through a cloud, compressing portions of it. The gravitational pull of a passing star or the slow rotation of the galaxy itself can nudge regions of the cloud toward greater density. Even the cloud's own internal turbulence can, in certain pockets, create small regions where gravity gains a temporary local advantage. Wherever gravity does gain that advantage, something remarkable begins. A denser pocket within the cloud begins to contract. As it contracts, its own gravity strengthens further, pulling in more surrounding material, growing steadily denser and hotter, a process that, once properly initiated, tends to reinforce and accelerate itself. This collapsing pocket of gas and dust is called a protostar. Over a period that can span tens of thousands to a few million years, a genuinely vast span of time by human standards, but comparatively brief on the scale of a star's eventual full lifetime, the collapsing material continues to compress under its own increasing gravity, converting gravitational energy into heat, growing hotter and hotter at its very center. Eventually, if the collapsing protostar has accumulated sufficient mass, a threshold of roughly 8% of the mass of our own Sun, something extraordinary happens at its core. The temperature and pressure at the center finally become extreme enough, several million degrees, to overcome the natural electrical repulsion between positively charged hydrogen nuclei, forcing them to fuse together into helium, releasing, in the process, an enormous quantity of energy. Nuclear fusion has ignited. A star is born. This moment marks a fundamental transition in the object's existence. The outward pressure generated by nuclear fusion at the core finally counterbalances the star's own relentless gravitational pull, halting the collapse and establishing the delicate, long-lasting equilibrium that will define the majority of the star's subsequent existence. Our own Sun formed through precisely this process, approximately 4.6 billion years ago, from a molecular cloud that also gave rise to the entire rest of our solar system. The planets, the moons, the asteroids, the comets, all of it condensing over a similar span of time from the same collapsing cloud of gas and dust that gave birth to our star. Every world in our solar system, our own included, is, in this specific sense, a sibling of the Sun, formed from the same original cloud at approximately the same time through the same fundamental gravitational process. We are, all of us, the leftover material of our own star's birth. Once nuclear fusion ignites at a star's core, that star enters what astronomers call the main sequence, the long, comparatively stable middle portion of its life, during which it will spend the overwhelming majority of its total existence. During the main sequence, a star maintains a remarkably steady equilibrium, sometimes described by astronomers as hydrostatic equilibrium, a continuous, precisely balanced contest between two opposing forces. Gravity, generated by the star's own considerable mass, constantly pulls inward, attempting to collapse the star further. The outward pressure generated by nuclear fusion at the core, pushing outward as a continuous stream of energy and radiation, precisely counterbalances that inward pull. For as long as the star has sufficient hydrogen fuel at its core to sustain fusion, these two forces remain in balance, and the star maintains a remarkably stable size, temperature, and overall structure. The specific nuclear process occurring at the core of a main sequence star like our own Sun is called the proton-proton chain. In simplified terms, it is a multi-step sequence in which 4 hydrogen nuclei are ultimately fused together to form a single helium nucleus, releasing energy at every step of the process. The mass of the resulting single helium nucleus is very slightly less than the combined mass of the 4 original hydrogen nuclei that fused to form it. That small, precise difference in mass is not lost or destroyed, it is converted directly into energy, following Einstein's famously precise equation relating mass and energy, and it is that specific, continuous conversion of mass into energy that ultimately powers the star, providing the light and heat that radiates outward, eventually, in our own sun's case, reaching the surface of Earth roughly 8 minutes after leaving the core. Our own sun converts approximately 600 million tons of hydrogen into helium in its core every single second. Despite this genuinely staggering rate of nuclear fusion, our sun contains such an enormous total reservoir of hydrogen fuel that it has already been burning steadily for approximately 4.6 billion years, and current astrophysical models indicate it has sufficient remaining fuel to continue burning in this stable main sequence state for approximately another 5 billion years. The specific duration a star spends on the main sequence, the total length of this stable, middle period of its life, depends critically on its mass, and the relationship, somewhat counterintuitively, runs in the opposite direction from what casual intuition might suggest. More massive stars, despite containing considerably more total hydrogen fuel than smaller stars like our Sun, burn through that fuel dramatically faster because their significantly greater mass generates significantly greater internal pressure and temperature at the core, driving nuclear fusion at a much more rapid, much more intense rate. A star roughly 10 times the mass of our Sun might exhaust its core hydrogen and complete its entire main sequence lifetime in a mere 20 or 30 million years, a remarkably brief span of time by stellar standards, even though it began its life with vastly more fuel than our Sun currently possesses. Conversely, smaller stars containing less total mass and therefore generating less internal pressure and heat burn their more modest hydrogen reserves at a correspondingly slower, more measured rate. The smallest, coolest, dimmest stars in the universe, called red dwarfs, smaller and cooler than our own Sun, but far more numerous throughout the galaxy, burn so slowly and so efficiently that current astrophysical models suggest some of them may continue fusing hydrogen for trillions of years, a length of time considerably longer than the current age of the entire universe itself. This means that a star's ultimate fate, precisely how it will eventually live out the remainder of its existence, and precisely how it will eventually die, is determined, in very large part, by a single fundamental property: the star's initial mass, largely fixed at the moment of its birth deep within its parent molecular cloud. No star, regardless of its initial mass, can sustain nuclear fusion in its core indefinitely. Eventually, inevitably, every star exhausts the readily available hydrogen fuel at its very center, and when this critical moment finally arrives, the extraordinarily stable, long-lasting equilibrium that has defined the majority of the star's existence begins, for the first time, to break down. Precisely what happens next depends significantly on the star's specific mass, but the general underlying pattern, at least in its broad outlines, is remarkably consistent across the vast majority of stars. As hydrogen fuel becomes genuinely scarce at the very core, the rate of nuclear fusion occurring there inevitably begins to decline. Because it is precisely this outward pressure from fusion that has been continuously counterbalancing the star's own persistent inward gravitational pull, any meaningful decline in fusion allows gravity to begin, for the first time in the star's long life, to gain a decisive advantage. The star's inert core, now composed predominantly of helium, the direct product of billions of years of continuous hydrogen fusion, begins to contract under the star's own unopposed gravity. As this helium-rich core contracts, it grows correspondingly hotter, exactly as our original protostar did many billions of years earlier, during the star's initial formation. This intensifying heat radiates outward into the surrounding layers of the star that still contain a meaningful reserve of unfused hydrogen. Those outer layers begin fusing hydrogen at a significantly accelerated rate, generating considerably more energy than the core alone had been producing throughout the star's stable main sequence lifetime. This sudden surge of additional energy causes the star's outer layers to expand dramatically, and as they expand, they cool. The star in this specific evolutionary phase swells enormously in overall physical size while its outer surface simultaneously cools and correspondingly reddens. The star has become what astronomers call a red giant. Our own sun, roughly 5 billion years from now, will undergo precisely this specific transformation. As it does, current astrophysical models suggest it will expand dramatically enough to potentially engulf Mercury and Venus entirely, and quite possibly Earth as well, though the exact details of Earth's specific fate remain a subject of some ongoing scientific debate and refinement, depending on precisely how much mass the Sun sheds during this particular transformation. For stars of relatively modest mass, roughly comparable to our own Sun, the core will eventually become hot and dense enough, despite containing no remaining hydrogen, to briefly ignite a secondary phase of fusion, converting the core's accumulated helium into carbon and oxygen. This secondary fusion phase, however, proves considerably shorter-lived than the star's original hydrogen-burning main sequence, and once the available helium fuel is similarly exhausted, the star has genuinely run out of any further nuclear fuel that it possesses sufficient mass and internal pressure to actually ignite. At this specific point, with no further fusion reactions remaining possible, the outer layers of the star, no longer meaningfully held in place by any significant internal pressure, drift gently outward into surrounding space, forming a strikingly beautiful glowing shell of expanding gas that astronomers somewhat confusingly call a planetary nebula, a name assigned centuries ago by early telescope observers who thought these glowing shells visually resembled distant planets, though the objects have no genuine connection whatsoever to actual planets. What remains behind at the very center of this expanding glowing shell is the star's original core, now an extraordinarily dense, slowly cooling remnant called a white dwarf. A typical white dwarf compresses roughly the mass of our own Sun into a sphere approximately the size of planet Earth, resulting in a material so extraordinarily dense that a single teaspoonful would weigh on Earth's surface several tons. This will be our own Sun's specific ultimate fate. Not a dramatic, catastrophic explosion, but a slow, gradual, comparatively gentle fade into a quiet, cooling ember, patiently radiating away its own remaining stored heat over what current models suggest will be trillions of years. But this quiet, comparatively gentle ending is very far from universal. For stars considerably more massive than our own Sun, the ending is a great deal more violent. For stars considerably more massive than our own Sun, generally those beginning their existence with at least 8 times the Sun's original mass, the story, once core hydrogen is exhausted, unfolds along a dramatically different and considerably more violent path, and it is precisely this specific path that ultimately produces most of the heavier elements that eventually make complex chemistry and therefore biological life possible at all. In these considerably more massive stars, the core's overall mass and correspondingly greater internal pressure allow nuclear fusion to continue significantly further than it ever could in a smaller Sun-like star. Once the available core helium is exhausted, converted into carbon and oxygen, the core's own gravity compresses it further still, generating sufficient additional heat and pressure to ignite carbon fusion, producing progressively heavier elements including neon, magnesium, and sodium. Once that further fuel source is similarly exhausted, the process, in a sufficiently massive star, repeats again. The core contracts further, grows hotter still, and ignites fusion of still heavier elements. This entire process, astronomers sometimes visualize it as resembling the concentric layers of an onion, with progressively heavier elements being actively fused within progressively deeper, hotter layers as you move inward toward the star's very center, continues in stages, each stage considerably shorter-lived than the one preceding it, right up through the fusion of silicon into iron. And it is precisely at iron that this entire elegant, self-sustaining process finally, irrevocably stops. Iron holds a genuinely unique position within the entire landscape of nuclear physics. For every single element lighter than iron, fusing two smaller nuclei together to form a heavier one releases net energy. This is precisely the fundamental process that has been powering the star throughout every previous stage of its life, from its very first ignition of hydrogen fusion onward. But for iron specifically, and every element heavier than iron, this relationship fundamentally reverses. Fusing iron requires more energy as an input than the fusion process itself actually releases as an output. This means that once a sufficiently massive star's core becomes predominantly composed of iron, it has, for the very first time in its entire life, genuinely run out of any further way to generate the outward pressure required to meaningfully counterbalance its own persistent gravitational pull. And because a sufficiently massive star's iron core can be built up with genuine astonishing speed, the silicon-to-iron fusion stage in the most massive stars can complete in a matter of mere days. The star's collapse, when it finally arrives, is correspondingly catastrophic and, on cosmic timescales, essentially instantaneous. The iron core, no longer meaningfully supported by any outward fusion pressure, collapses inward with tremendous sudden violence in well under a single second. Protons and electrons throughout the collapsing core are forced together with such extraordinary violence that they combine to form neutrons, releasing an enormous, sudden burst of subatomic particles called neutrinos. The core's collapse, moving at a meaningful fraction of the speed of light, does not simply continue indefinitely. It eventually halts abruptly once the core reaches the extraordinary density of a neutron star, and that abrupt, violent halt sends a powerful shock wave rebounding outward through the remainder of the star's outer layers. This rebounding shockwave, combined with the star's own now unleashed burst of neutrinos, together drive one of the single most energetic, most violent events the observable universe is capable of producing, a core collapse supernova. For a brief period, sometimes lasting mere days or weeks, the exploding star can genuinely outshine every single other star within its entire host galaxy combined. And it is precisely within the extraordinary extreme conditions of this specific explosive process, conditions of heat, pressure, and raw energy far beyond anything that could ever be sustained within an ordinary, stable stellar core, that many of the heaviest, most complex elements in the entire universe are finally, definitively forged. The extraordinary flood of neutrons released during the initial collapse can rapidly, repeatedly bombard existing atomic nuclei within the exploding star, building up in a process astrophysicists call rapid neutron capture many of the heaviest elements found anywhere in nature, including gold, platinum, and uranium. This single, violent, catastrophic event does something else profoundly significant as well. It violently disperses the entire accumulated chemical inventory of the star's death. All of that carefully layered carbon, oxygen, silicon, iron, and every other element painstakingly forged across the star's entire lifetime, together with the additional heavy elements freshly created within the supernova explosion itself, outward into the surrounding interstellar medium, seeding that same molecular cloud material we began tonight's story with, ready, in time, to be incorporated into an entirely new generation of forming stars and forming planets, and, eventually, life. Every atom of gold ever mined from the earth, every atom of iron in your blood, every atom of calcium in your bones, forged inside a star, and then, at that specific star's moment of catastrophic death, violently flung outward across the galaxy, patiently waiting, across billions of subsequent years, to eventually become part of you. Chapter 6. The star that might be about to do this again. Anomaly 3. Betelgeuse and the watch for the next supernova. Roughly 640 light-years from Earth sits a star that offers a genuinely rare, genuinely valuable opportunity. The chance to watch this entire dramatic process unfold in something approaching real time from remarkably close cosmic proximity. Its name is Betelgeuse, and it forms the distinctive reddish shoulder of the constellation Orion, clearly visible to the naked eye on any sufficiently clear night. It is what astronomers classify as a red supergiant, an extraordinarily massive, extraordinarily aged star currently somewhere between 10 and 20 times the mass of our own Sun that has already progressed well beyond its original main sequence hydrogen-burning phase and into the later, considerably more advanced, considerably more unstable stages of stellar evolution we have been discussing throughout tonight's episode. Betelgeuse is genuinely enormous. If it were somehow placed at the exact centre of our own solar system in place of our Sun, its outer surface would extend outward past the orbit of Jupiter. And, based on current, careful astrophysical understanding of stellar evolution, Betelgeuse is very likely nearing the genuine end of its life, meaning it is a strong candidate to undergo a core collapse supernova at essentially any time, astronomically speaking, though any time in this specific context could reasonably mean anywhere from tomorrow to 100,000 years from now. In late 2019 and into early 2020, Betelgeuse experienced a dramatic, widely reported dimming event, growing noticeably fainter than astronomers had ever previously recorded. This sudden, unexpected change generated considerable genuine excitement and no small amount of speculative media coverage regarding the distinct possibility that the star might be entering the immediate final stages preceding a supernova explosion. Subsequent, more careful analysis determined that this specific dimming event was most likely caused by a large cloud of dust expelled from the star's own extended, unstable outer atmosphere that briefly obscured a meaningful portion of Betelgeuse's light as observed from Earth, rather than being a direct, immediate signal of imminent core collapse. Betelgeuse's brightness has since gradually returned to something closer to its previously typical range. More recently, in ongoing observations continuing into 2026, astronomers have continued monitoring reports of unusual, still not fully explained changes in Betelgeuse's overall brightness and pulsation pattern, consistent with a star genuinely nearing, though not necessarily immediately at, the very end stages of its stellar life. Current, careful astrophysical consensus holds that Betelgeuse is indeed likely to explode as a supernova at some point within the next 100,000 years, a span of time that, while unmistakably vast by ordinary human standards, is remarkably, meaningfully brief when measured against the star's own multi-million-year total lifetime. When Betelgeuse does eventually explode, the resulting supernova, based on current astrophysical models and its relatively close proximity to Earth, is expected to become extraordinarily bright as observed from our planet, potentially bright enough to be clearly, easily visible even during full daylight hours for a period of several weeks, and bright enough at night to cast faint visible shadows on the ground, despite the star's genuinely enormous distance of 640 light-years. It is worth being entirely clear and precise on one specific point. Betelgeuse's eventual supernova poses no meaningful danger whatsoever to life on Earth. It sits far too distant for any of the explosion's most immediately harmful radiation to meaningfully reach us in any dangerous quantity. What it offers instead is something considerably rarer and, in its own way, considerably more valuable, a genuine, extraordinary opportunity for humanity to directly observe, in real time, exactly the kind of element-forging cosmic event that ultimately created the very atoms making up our own bodies. The same fundamental process we have been carefully tracing throughout this entire episode, potentially unfolding directly within a single human lifetime, clearly visible to anyone who simply looks upward into the night sky. We do not know precisely when Betelgeuse will finally explode. It could be tomorrow night. It could be considerably further in the future than any of us or several subsequent generations after us will ever personally witness. but somewhere in the constellation Orion, a star that helped inspire in its own small way tonight's entire journey through stellar life and death, is quietly, patiently approaching precisely the kind of ending that once, long ago, in some other now-vanished star, ultimately made you. Despite the genuinely remarkable, well-established precision of our overall understanding of stellar evolution, precision detailed and confirmed enough to allow astrophysicists to confidently predict centuries and even millennia in advance the eventual specific fate of stars based primarily on their initial mass, several genuine, actively debated mysteries remain, sitting at the very frontier of current stellar astrophysics. The first significant open question concerns the exact, precise mechanism driving core collapse supernovae themselves. While the overall broad picture we described a few chapters ago, core collapse, neutron formation, a rebounding shock wave, is well understood and firmly established in its general outline, the specific detailed physics of precisely how that initial rebounding shock wave successfully reverses its own direction and ultimately successfully blows apart the star's considerable remaining outer layers has proven genuinely difficult to fully model with complete confidence. Early computational simulations of this specific process frequently found that the initial shockwave tended to stall partway through the star, its own energy gradually absorbed by the surrounding infalling stellar material, rather than successfully continuing all the way outward to produce a fully successful, complete explosion. Considerable subsequent theoretical and computational work, incorporating increasingly sophisticated treatments of neutrino physics and complex three-dimensional fluid turbulence within the collapsing star, has made substantial genuine progress toward resolving this specific stalled shock problem. But the precise, complete details of exactly how every core collapse supernova reliably succeeds in fully exploding remain an active, ongoing area of dedicated theoretical astrophysics research. A second, closely related open question concerns the precise, exact boundary separating stars that ultimately collapse into neutron stars from those that instead collapse further still into black holes. The general, broad picture is reasonably well understood. Sufficiently massive stellar cores collapse into neutron stars, while even more massive cores collapse further into black holes. But the precise, exact mass threshold separating these two dramatically different outcomes has proven considerably more difficult to pin down with complete confidence than early, simpler theoretical models originally suggested. And current astronomical observations have identified various specific stellar remnants whose measured masses sit uncomfortably within what astrophysicists sometimes informally call the mass gap, a specific range of masses that current stellar evolution models struggle to confidently explain as the product of either a neutron star or a black hole formation process. A third, considerably more recent and genuinely still emerging area of active astrophysical research concerns the specific behavior of the very first generation of stars ever to form in the universe. Stars astronomers refer to as population 3 stars, composed almost entirely of pure, unenriched hydrogen and helium condensing directly from the primordial gas remaining after the Big Bang itself, entirely lacking the heavier elements that, as we discussed earlier tonight, are only produced by previous generations of stars. Current theoretical models suggest these earlier stars may have been dramatically more massive and correspondingly far more short-lived than any stars forming in the present-day universe. No confirmed direct observation of an individual population 3 star has yet been made, though the James Webb Space Telescope, discussed in an earlier chapter of this series, has been specifically searching for indirect signatures of their presence within the very earliest, most distant galaxies it has so far been able to detect, and several recent tentative candidate observations, still requiring further confirmation, have generated genuine, considerable excitement within the astrophysics community. None of these specific open questions meaningfully undermines the overall well-established framework of stellar evolution that we have carefully traced throughout tonight's episode. They represent, instead, precisely the kind of genuine, honest frontier that characterizes any healthy, active area of ongoing scientific research, a well-established, thoroughly confirmed core framework surrounded by specific, genuinely interesting, actively studied questions of important remaining detail. The specific idea that stars themselves might be responsible for actually creating the heavier chemical elements is a considerably more recent scientific development than many people initially assume, and its own history offers a genuinely worthwhile final piece of context before we close tonight's episode. For a very long stretch of scientific history, the fundamental question of precisely where the universe's heavier chemical elements actually originated remained genuinely, deeply unresolved. 19th century and early 20th century physicists understood a reasonable amount about the basic properties of individual chemical elements, but had no clear, coherent, well-supported theoretical framework for explaining how those specific elements might have originally come into existence in the first place. The specific theoretical breakthrough arrived in 1957 with the publication of a landmark, genuinely foundational scientific paper titled, with characteristic mid-century scientific directness, simply Synthesis of the Elements in Stars. It was authored by 4 scientists working in close collaboration: Margaret Burbidge, Geoffrey Burbidge, William Fowler, and, notably, Fred Hoyle, the very same astronomer who, as we discussed in the previous chapter of this series, had somewhat dismissively coined the term Big Bang, while simultaneously making some of the most genuinely important foundational contributions to an entirely different, closely related area of astrophysics. This landmark paper, subsequently referred to informally within the field simply as B²FH, after the initials of its 4 listed authors, laid out in careful, systematic, comprehensive detail precisely the process we have carefully traced throughout tonight's entire episode. How nuclear fusion within ordinary stellar cores progressively builds up increasingly heavier elements, layer by layer, stage by stage, right up to iron, and how the extraordinarily extreme violent conditions specifically generated during a supernova explosion are additionally required to successfully forge the remaining, even heavier elements found throughout the periodic table. The paper represented an extraordinary, genuinely comprehensive synthesis of contemporary nuclear physics and observational astrophysics, and it fundamentally, permanently transformed our overall scientific understanding of precisely where the chemical elements that make up our own physical bodies, and indeed every single object in the observable universe, actually originally came from. William Fowler would go on to receive the Nobel Prize in Physics in 1983, specifically recognizing this foundational body of work, though in a decision that remains, to this day, one of the more widely and openly debated omissions in the entire history of the Nobel Prize. Fred Hoyle himself was controversially not included as a co-recipient, despite having made genuinely essential foundational contributions to the very same landmark paper. What this specific 1957 paper collectively established, and what subsequent decades of continued careful astrophysical research have since progressively refined and confirmed with ever greater precision, is a genuinely elegant, complete cosmic cycle. Stars form from collapsing molecular clouds. Stars spend the great majority of their total existence steadily fusing hydrogen into helium. As stars age and eventually exhaust their core hydrogen fuel, they progressively fuse increasingly heavier elements in stars of sufficient initial mass right up to iron. Sufficiently massive stars then die in catastrophic supernova explosions, simultaneously forging the very heaviest remaining elements and violently scattering their entire accumulated chemical inventory outward across surrounding interstellar space. That freshly scattered material subsequently enriches nearby molecular clouds, which then, in time, collapse to form an entirely new generation of stars, and, crucially, an entirely new generation of planets, considerably richer in heavier elements than any previous generation, orbiting those newly forming stars. Our own sun is what astronomers specifically classify as a third-generation star, meaning it formed from material that had already been processed and enriched by at least two, and quite possibly several more previous generations of now long-vanished stars. This specific classification is precisely why our own solar system contains a meaningfully rich abundance of heavier elements, sufficient carbon, oxygen, silicon, iron, and countless other elements to form rocky planets, and eventually, on at least one of those rocky planets, to form the specific chemistry of life itself. A genuine first-generation star forming directly and exclusively from the primordial hydrogen and helium remaining immediately after the Big Bang would have possessed none of these essential heavier elements and consequently could never have given rise to rocky planets or, presumably, to anything resembling the specific chemistry required to eventually support life as we currently understand and define it. You exist, in a very real and quite literal sense, because multiple previous generations of stars, over billions of years of cosmic history, patiently lived out their own individual lives, and then, in their own individual deaths, generously provided the essential raw chemical material required for the next generation to eventually form. There is a particular specific quality to this particular piece of scientific knowledge that sets it apart in an important way from many of the other genuine mysteries we have carefully explored together throughout this series. Most of what we have discussed together across these various episodes, the search for extraterrestrial life, the precise expansion rate of the universe, the true underlying nature of dark matter, the deep, genuine mystery of what happens at the very center of a black hole, the honest limits of what we currently know about the universe's ultimate beginning, represents genuine, active frontiers of ongoing human knowledge. Questions we do not yet have complete, satisfying answers to, places where our current best physics runs directly up against the honest limits of what it can currently confidently tell us. The story of stellar nucleosynthesis, the specific, detailed process by which stars actually create the heavier chemical elements, is different in one genuinely important respect. It is not in its fundamental broad outline a mystery any longer. It is a settled, thoroughly confirmed, remarkably well understood scientific fact, verified through decades of careful, converging observational and theoretical astrophysics. And it happens to be a settled fact that says something genuinely profound and genuinely worth sitting with quietly about your own specific, individual, personal existence. Every atom of carbon in your body was forged, without exception, inside the core of some now long-vanished ancient star. Every atom of oxygen you have breathed throughout your entire life, and every atom of oxygen you will continue breathing for the remainder of it, was manufactured through precisely the same fundamental stellar nuclear process. Every atom of calcium currently supporting your skeleton, every atom of iron currently carrying oxygen through your bloodstream at this exact moment, was forged specifically within the violent, extraordinary, extreme conditions of some ancient star's own final catastrophic death throes. This is not merely a comforting, poetic way of expressing a much simpler underlying scientific idea. It is the single most literal, most precisely accurate possible description of your own actual physical origin that modern physics is currently capable of offering. The specific carbon atoms currently forming the DNA inside every single cell throughout your entire body have existed in one continuously changing physical form or another for literally billions of years, tracing an extraordinary, unbroken physical journey, forged deep within some now vanished star's ancient nuclear core, violently scattered outward across the galaxy during that specific star's own catastrophic death, patiently drifting through the cold vacuum of interstellar space for millions or even billions of subsequent years. eventually gathering together with other such scattered material to help form our own particular molecular cloud, condensing along with the rest of that cloud into our own specific solar system, becoming incorporated into the young, forming Earth, and then, considerably later, through the patient, unhurried processes of chemistry and biological evolution unfolding across billions of subsequent years, eventually becoming part of you. You are reading, or rather, quietly listening to, these specific words using a brain built from stardust. You are breathing right now using lungs built from stardust. Your own heart, quietly and steadily beating throughout this entire episode, pumping blood carrying iron forged specifically within some ancient, long-vanished star's own final violent moments, is itself built entirely from stardust. Carl Sagan, the astronomer and celebrated science communicator, once famously observed that we are, in the most literal sense available to physics, made of star stuff. It is worth being genuinely precise about this specific claim, rather than simply accepting it as comforting poetry. It is not merely a beautiful, evocative way of expressing some vague, general sense of cosmic connection or belonging. It is a direct, specific, quantitatively verified consequence of decades of careful, rigorous nuclear astrophysics, tracing the exact origin of every single element heavier than hydrogen and helium currently found within your own physical body back to the specific nuclear furnaces of long-vanished ancient stars. Tonight, somewhere out there in the vast darkness beyond our own atmosphere, other stars are continuing this same ancient ongoing process. New stars are steadily, patiently forming from their own molecular clouds. Others are quietly, gradually approaching the natural, inevitable end of their own individual stellar lives. And somewhere else out there, right now, at this very moment, some sufficiently massive, sufficiently aged star, not unlike Betelgeuse, may well be approaching its own final catastrophic moments, preparing, in its own violent, spectacular death, to forge and scatter the specific raw chemical material for some entirely new generation of stars, and perhaps, given sufficient additional time, entirely new planets, and perhaps, given even more time still, some entirely new, currently unimaginable form of life. We are not simply observers of this ancient, ongoing cosmic process. We are, each and every one of us, without exception, its direct, physical, chemical product. The universe spent well over 9 billion years before our own sun even formed, patiently building and rebuilding stars over and over again across countless successive generations before it had finally accumulated sufficient heavier elements to eventually make something like you even remotely possible. Tonight, as you finally drift towards sleep, you carry within your own body the complete physical legacy of that entire patient billion-year cosmic process. Every single atom of you has already been, quite literally, inside a star,